As we begin to start Chapter 8, we're going to be talking about right triangles and trigonometry. And in Lesson 8.1, we're going to talk about our similarity in right triangles. So if you take a look at our diagram here, my overall triangle, or my large triangle, JKL, I can see that sketched in, I have an altitude. And my altitude would be this segment right here. My altitude is the height of the triangle. It meets the base at 90 degrees. So it says that the altitude to the hypotenuse of a right triangle forms two triangles that are similar to each other and to the original triangle. So when we draw in the altitude to from the vertex to the hypotenuse, we actually have three triangles that are formed. A small triangle, medium triangle, and then the overall larger triangle. And what happens is that all three are similar. So we're just going to work on a little bit of our visualization skills. If I asked you to write a similarity statement for those three triangles, we would need that to be in corresponding order. Some people could look up this diagram and maybe do that on their own. However, it can be a little bit tricky. They show down below taking the three triangles, kind of drawing them separately, but drawing them so that they have the same orientation. So in this case, we see that the right angle is kind of in the bottom right-hand location. And that way, it becomes much easier to write the similarity statement. Triangle LJK, similar to JMK, similar to LMJ. They started with the short leg, long leg, and then the hypotenuse. So we're just going to practice that. If you take a look down below at example A, I'm asking you to write a similarity statement comparing the three triangles in the diagram. Again, you may be able to do this without sketching the triangles separately, but I do think it makes it a little bit easier. I'm going to take my large triangle, VWU. I'm going to do the same thing as above, and I'm going to put my right angle in kind of the bottom right corner. And I'm going to sketch all of these triangles so that they all have the same orientation. So basically, I'd be taking this and I'd be rotating it, VWU. And I know that W is my 90-degree angle. Now, in my medium-sized triangle, I see the right angle here happens at Z. So I'm going to draw this. I know I'm going to have long leg, short leg, and hypotenuse. Here's my right angle, and I know that is Z. Now I just need to figure out where my other two vertices go. Well, my short leg in there is ZW. So this is going to have to be ZW. And the long leg over here would be U. Now for my smaller triangle, again, the right angle is going to be happening at Z. So I know that goes here. My short leg is ZV. So I know V would go here. And then this other, the long leg ZW. So once I have my triangle sketched separately, and it makes it, and my vertices labeled, it makes it much easier to write my similarity statement. I am going to go short leg and long leg hypotenuse. So I'm going to say triangle VWU is similar to WCU, similar to VZW. Now again, your similarity statement could look different. It could be in a different order, but the vertices need to correspond. Okay, if you flip your paper over, the other topic I want to talk about in 8.1 is the geometric mean. Now when we hear the word mean, we kind of think of mean, median, mode, and range, and those are all measures of central tendency. But did you know there's actually two different means? You can talk about having the geometric mean or the arithmetic mean. Most of us are familiar with the arithmetic mean, the average, in which we just add our data points up and divide by how many there are. But there is a geometric mean as well. The geometric mean is a measure of central tendency, so it's kind of a summarizing number. But it will always be equal to or less than the arithmetic mean. Well, what is the geometric mean? Well, it is defined as the nth root of the product of n numbers. That can be a little bit confusing, but the product of n numbers, the nth root. Well, if I have the geometric mean of AB, we would be multiplying them, we get the product. And the nth root, if there are two numbers, then we need the square root. And so here, my geometric mean for AB would look as so. Now, if I have three numbers, I'm going to call those A, B, and C. It would be the product of A, B, and C, but it would be the cubic root. Today, we are only going to work with two numbers, finding our geometric mean, but we're also going to work on simplifying our radicals. So if I look at question number 1, I want the geometric mean for 4 and 9. Well, we know it's the product of nth root of the product of those numbers. Well, that would just be the square root of 36, which is a perfect square. Our geometric mean would be 6. If I take a look at finding the geometric mean for 7 and 20, well, 7 times 20 is 140, and 140 is not a perfect square number. But we can break it down a little bit. We can simplify. We're going to give our answer in radical form. 4 actually goes into there 35 times. And if you remember, I can break that up, the square root of 4 times the square root of 35, for a final answer of 2 root 35. That would be simplest radical form. 5 and 30, well, 5 times 30 is 150. The square root of 150 is not a perfect square, but it can be broken down. We can break that down into 25 times 3. And the square root of 25 is 5. We're left with our root 3. Final answer of 5 root 3. Down below, you'll see that there are a couple corollaries mentioned here. How do these two topics tie together? Well, it just so happens that this altitude here in my right triangle, H, it is the geometric mean of the way my hypotenuse is divided x and y. So my length for H would be the square root of x, the product of x and y. And likewise, there are some similar corollaries that are true for the side lengths of that large right triangle. I'm not going to make you memorize the corollaries, and I'm not going to spend a lot of time focusing on them, but I just wanted to introduce to you the topic of geometric mean and also review some simplifying radicals.